Alright, today we are talking about our last graph theory topic, and that is on directed graphs. So these are graphs whose edges have arrows or an orientation to them. Before we jump into that too much though, I'm going to backtrack a little bit and talk a bit about circuits, which we were talking about last time. So one trend that I hope you saw in class was that in general, so for example, let's just take an arbitrary graph of maybe 12 vertices. In general, if that graph has more edges, then it's going to be easier for the graph to be Hamilton. In other words, it's going to be easier for us to be able to find a path that hits every vertex exactly once. Let's walk through a theorem that codifies that idea. So let's take a graph, and let's say that our graph has at least 3 vertices. For 2 or fewer vertices, we often don't even have circuits, so we're just ignoring those cases. Our graph has at least 3 vertices, and if it's the case that we have a lot of edges. And in this context, what I mean by that is that every vertex has at least v over 2. In other words, if our graph had 12 vertices, we're saying that each vertex has at least 6 edges coming out of it. Okay. So if a graph has at least this many edges, so if a graph has this property, then there must always be a Hamiltonian circuit somewhere in that picture. So if a graph has this property, then it must be the case that that graph somewhere in it has a Hamiltonian circuit. And the proof of this illustrates a few ideas that we've talked about before. It actually brings some pigeonhole principle ideas into it, so we're going to walk through that proof as well. First step in the proof is pointing out that our graph is connected. And one way to see that is we can ask ourselves, all right, if our graph wasn't connected, let's say we had something like this where we have some number of vertices in one group and some number of vertices in another group, so if our graph was not connected, then it can't possibly be the case that every vertex is connected to at least v over 2 vertices, because we can take whatever the smaller group is and point out that, hey, it has to have fewer than that edges coming out of it. Alright, so it must be the case that our graph G is all one piece, so maybe it looks more like this instead. So let's take P to be the longest path that we can find in our graph G that doesn't repeat any of our vertices. So maybe we start here and work our way through. Hey, there we go. That's a reasonably long path that doesn't repeat any vertices. So there might be many paths that don't repeat vertices. We're just picking one of those paths that is as long as possible, that includes as many vertices as possible. This is actually a common technique in a lot of proof writing. We take something, assume that it's the biggest it can possibly be, and use the fact that it is as big as it could possibly be to prove something or another. So we're going to use this fact in a moment that this path is the longest it can possibly be. So what does this graph look like? Well, we know that it has many edges. There are going to be a whole bunch of edges floating around, but we're ignoring those for now. Let's first say, all right, we have exactly this. We have a path going from vertex 0 through vertex k, so we know that we have at least these edges. So we don't know how long the sequence is, it depends on what k is, but we know that at least we have this picture. Our goal is to show how to rearrange or transform this path P to get it to look like a Hamilton circuit. So we don't know what these edges are doing coming out of most of these vertices. However, because this path is as long as it can be, we know that it can't be the case that some other vertex is adjacent to v0 that isn't one that we've already mentioned. In other words, all of the adjacencies to v0 have to be vertices that are already mentioned in this list. Otherwise, if there was some other vertex here that was adjacent to v0 that wasn't mentioned, then hey, we now have an even longer path. And this contradicts our assumption that P was the longest path that doesn't repeat any vertices possible. So since all of v0's adjacencies lie somewhere in this path, and since v0 has at least v over 2 adjacencies, it must be the case that v0 is adjacent to at least v over 2 of these vertices. Right? So all of its connections have to appear somewhere in this list. Since it has at least v over 2, it must look something like this. The same must be true for vk. All of its connections are to vertices that previously showed up in our path, and it has at least v over 2 connections. Therefore, there are enough total connections that by the pigeonhole principle, it must be the case that at some point, so let's call this vertex vi, at some point, vi is connected to vk, and v0 is connected to vi plus 1. You should think through for yourself why exactly the pigeonhole principle implies this, but it essentially amounts to the fact that there are too many connections that have to exist. We've only drawn a few of them here. There are too many connections that have to exist for this to not be the case. Again, remember, there are probably many, many other edges that show up in this graph. We're just focusing on these because these are the ones that we need in order to find this Hamiltonian circuit. So the last step is just to point out that now that we have these connections, we can reorder this path rather than going from v0 to v1 to v2, etc., to use vi and vi plus 1 as a way of looping back. It's not necessarily the case that v0 and vk have a connection. So we can't just say, hey, take the longest path and then end up back where we started. We don't necessarily know that that's true. But we do know that somewhere in there, somewhere in this path, is a vi that has this property, where vi joins the last one and vi plus 1 joins the first one. Because of this, here is our circuit. We start at v0, we work our way all the way to vi, then we jump to the end and work backwards. Then that last piece, that vi plus 1, we know connects to v0. Therefore, that is our Hamilton circuit. So here's a way of writing out what I just said. We have our v0 through vi piece, then we jump to the end, and we have vk down through vi plus 1, and then we end up back where we start with v0. So this is a circuit. I called it a Hamiltonian circuit a moment ago. We haven't yet shown that it hits every vertex. Well, what if it didn't hit every vertex? What if there was some other vertex out there that it's missing? And because our graph is connected, that vertex has to connect somewhere into our picture. We already said why it can't connect to the end, but maybe it connects to somewhere not on the end. Well, now that we have this circuit, now that this path can close back up, we can use this. So if this situation existed, then we can find a new longest path. Namely, we can trace back and tie into our circuit and find a path that was in fact longer than our original starting P. The whole point was that this original path, this original sequence v0 through vk, was as long as it possibly could be. If there were any other vertices out there, we could use this to find an even longer path. So since P is as long as it possibly is, this must contain all of the vertices, so we can't have any extra pieces. So this path hits all vertices and hits them only once. Therefore, it's Hamilton. So there's our last part written down, and that concludes our proof that as long as every vertex has valence at least this v over n cutoff, and that our graph has at least 3 vertices, it must have somewhere in it a Hamiltonian circuit. In theory, this is a video about directed graphs, so let's actually talk about directed graphs. So our normal graph, as we said on day 1, was a collection of vertices and edges. So if we have A, B, and C, we can say that our graph is the set of elements A, B, and C, and then our edges are the set of connections or pairs of vertices. A directed graph is when we put an orientation on each of the edges. So we say that the edge AC is oriented to go from A to B. We say that it's going out of A and into C. It's going from A to C. So rather than listing our edges just as elements and sets, we want them as ordered pairs A, C, rather than just the elements A and C. All right. So if we give each of the edges an orientation, what we're left with is a directed graph or a digraph. So in practice, many of the applications that use graph theory also carry with it some sort of notion of direction or order to how maybe you would move through a graph. And so giving edges direction, giving them an orientation, can help us model whatever system it is that we're working with. Often one of the reasons that we're discussing directed graphs is because we are trying to navigate the graph, as in we're trying to go for a walk through a graph. And when we're doing this, typically the rule is that any traversing of this graph must follow the direction. We can think of these arrows as being one-way streets. When working with directed graphs, it often makes sense to pay attention to the valence of each vertex, but through the lens of counting which way the edges are going. So in light of that, we'll define the invalence, or generally more commonly the in-degree, to be the number of edges pointing towards a certain vertex v. So in our example here, we have a graph where the valence of each of the three vertices is 2. However, the invalence differs from vertex to vertex. A total of 2 edges are pointing at B, therefore we say the in-degree of B is 2. Similarly, only 1 edge is pointing at C, and no edges are pointing at A, therefore the in-degree of C is 1 and the in-degree of A is 0. In much the same way, we can define the outvalence or out-degree of a certain vertex. It's just the number of edges that are leaving that vertex. So in our example here, A would have out-degree 2, whereas B would have out-degree 0. In this particular example, for each vertex, the in-degree plus the out-degree was the same for all the vertices, but certainly that doesn't necessarily have to be true. I'll leave it to you and your groups to discuss what relationship there is amongst this out-degree and in-degree properties. Last definition here, a tournament is a complete directed graph. So remember, complete means that however many vertices we have, we include all of the edges between those vertices. So here is the complete graph with 4 vertices. And digraph just means that we put arrows on them. So this is a complete graph, but if I give it arrows, if I add a direction to each of the edges, I now have a tournament. It's worth mentioning that when it comes to just complete graphs, we can just say K4 and we know exactly what it is we're talking about. Since we're now working with tournaments, or the directed versions of those, K4 is a little ambiguous because we also need to specify the direction. So there are many tournaments on 4 vertices, whereas there is only one complete graph on 4 vertices. As always, I'll have you work on these in groups and just to try to get a feel for what kinds of questions we can ask about things like directed graphs, or more specifically tournaments. These tournaments are going to be useful for us when we start talking about voting systems in our last week of classes, but it's also worth mentioning that other directed graphs, specifically acyclic graphs, so directed graphs that don't have cycles like this one, are used in a number of different applications. We aren't going to talk much about those, mainly because we're running out of time in the semester, but it's worth mentioning that there are quite a few applications for these directed graphs.